Okay, welcome to PL Background Part 2. So I wanted to start by talking a little bit about where this is all going now that you've had a taste for what we'll be talking about. So the theme of this year's OPLSS, to the extent that there is a theme, one thing we could call it is language-based techniques for reasoning about programs. And we'll see a few different styles of these techniques, including the kind of operational techniques or logical relations that Bob was talking about in the previous lecture. And we'll see some techniques based on denotational or semantics. And then later in the school, particularly in the last set of lectures, we'll see more stuff on specification logics for imperative and concurrent programs. So the way this is sort of divided is that in the second block and third blocks of lectures, we'll see applications to parametricity. We'll start that off tomorrow. And network programming. So Nate Foster is going to do a course on that. And efficiency, that is reasoning about how long programs take to run. And then in block 3, we'll see things on refinement types and concurrency and compiler verification. Bob alluded to that earlier. All right, so we've got kind of a broad spate of different topics in programming, and we're going to learn how to reason about all of these different topics. But to do that, what we really need to do is to boot up here on programming languages and category theory in block 1. So what we've tried to do is to basically condense a couple of semester-long courses into about 12 lectures or whatever for these first 4 days. So there's going to be a lot to digest. And the thing I want to say, I mean, Zaina said it and Bob said it, but my point of view of this is it's really important that our goal here is that everyone learns something, not that there's something that everyone learns, right? So depending on where you're coming in, we have people coming in with lots and lots of different backgrounds, lots of different experience coming in. Start from where you are, and I hope you'll get something over the course of the school. If you don't have very much background in all of this stuff, maybe what you get is sort of a taste of this, and then let this wash over you, and the lectures will be online, the assignments will be online, you can look at it after, right? If you're already a fourth-year PhD student and all of this stuff is all old hat, then we've got this coming up, so bear with us for the first few days, and I really hope that you'll help out your peers here and work with them on kind of doing the assignments and stuff like that. So in the assignments we've prepared, particularly for the PL background, there's way more problems for the hands-on session than you'll be able to do before tomorrow or before next week even. But so I just hope you'll kind of take a stab at one. You'll have to pick and choose your battles and decide what you want to work on. But there's a lot there, and I just hope you'll sort of find your way through it to learn something. Okay, so with that said, now I want to move on to some of the more technical stuff. So picking up from where Bob was, for today, what I'm going to do is to talk about one main component of reasoning about programs. In particular, what's called equational reasoning. And the idea is that you might want to, for example, have two pieces of code, which we'll call the fast implementation and the slow implementation. Slow is also sometimes called the reference implementation. And the question you want to ask is, are these two pieces of code the same. So you've got some problem, like maybe your problem is sorting, and here you have merge sort, and here you have insertion sort, just to take like the simplest little functional programming example that I can think of. The idea is that you've got a problem you want to solve, sorting. You've got two different ways of solving it. The question we're going to develop technology to answer is, are they the same? Why is that a good question to answer? Yeah? Because it's probably easier to prove your reference correct. Exactly. So why did we write insertion sort? Well, it's a really simple, structurally recursive way to do sorting. It's obvious that it produces a sorted list, or it's at least easier to prove that it produces a sorted list. One way to reason about your faster, more complicated piece of code is to then say that that piece of code behaves the same as this other one that I've proved correct. In other circumstances, you might take this kind of thing as the definition of what it means to be correct. Right? So like there's a lot of problems in programming where there's a way to solve it in sort of an obvious or brute force or slow kind of way. And at least that, OK, you're like, OK, yes, it solves the problem. But then what the game is figuring out a faster or more efficient way to do it. And you want to think about, is that behaving the same as the reference implementation? OK? So the question you want to ask is one piece of code the same as another? And then as programming languages people, what we have to ask is, what does that even mean? And how do you prove that two pieces of code are the same? Okay? And this kind of equational reasoning is going to be a subcomponent of all of the logical or denotational ways of verifying programs that we'll see later in the school. So it's kind of the very foundation is this idea of equational reasoning. So what we need to do is we need to define when are two programs equal. And right, it's kind of a funny question, because usually in math you sort of take it as a given what equality means. But here it's pretty subtle to figure out what it means for two programs to be equal. So my first cut at it is that two programs are equal if and only if you can't tell them apart. OK? All right, so like I just double negated, which really doesn't explain anything. But it does sort of lead towards the definition that we'll use. So first of all, what I want to say is for two closed programs of type int. OK, so I'm going to assume, like in Bob's lecture, that we have function types. But instead of natural numbers with 0 and successor and recursion, just to simplify things and get things out of the way a little, let's just assume that we have int, which is treated as a base type, with numeric constants k, so I mean like 1, 2, 3, et cetera, and that we have e1 plus e2 as a built-in. And this just gets some of the stuff about the recursor out of the way for today's lecture. One of the exercises for the hands-on session will be doing all of this for nat instead of int. So now if that's my base type, then what I'm going to say about two closed programs of type int is that e1 is e is equal to e prime if and only if there is some number such that e runs in some number of steps to k, and e prime runs in some number of steps to the same k. Okay? So not being able to tell apart two closed programs that have a base type like int just means they run down to the same answer. If this one runs to 3, that one runs to 3. If this one runs to 4, that one runs to 4. If this one runs to 3 and this one runs to 7, then they're not equal. Okay? So now we want to lift that to higher order. And so I need a little more room here. what I'm going to do is to define a program context, which I'll write as kind of a scripty P, to be an expression with one variable of type tau that has type int. And that one variable of type tau, I'm going to write that as a circle because we'll call that the hole in the expression. Okay? So what this is going to look like, for example, might be hole plus 1 and then 2 plus that. Okay? So that's a context where with a hole, it has type int. What's the type of the hole here? What would I need to plug in for that variable in order for this whole thing to be well typed? Int. On the other hand, I might have a context where I have the hole applied to 7 plus 1. What type would that hole need to have? Good. Right, so the hole can be of any type, but in a program context, the overall context has type int. The idea is it's a way of taking a value of a type, tau, and making a complete program out of it. And what I'll write is, just to simplify things, P brackets E means plug in E for the hole in the context. Okay, so that's filling the hole with a particular expression. So now the idea of two programs are equal if you can't tell them apart is that for E prime of type tau in general, not just int, E is going to be what we'll write as observationally equal to E prime if and only if for all contexts, program contexts P, where the hole has type tau means that P has type int, what we have is that P filled with E is that P filled with E prime. So this one right here gets pronounced as clean E equivalence. So that's the one that says for two programs that have the base type int, they run to the same thing. Okay? And now our notion of two programs of some type other than int, two programs of type int arrow int or int arrow int or anything like that are equal. What does it mean that we can't tell them apart? Well, the way we're going to say we can't tell them apart is any bigger program that you put them in, that's what the P represents. If you take these two programs and put them into a bigger program, then the results are the same number, right? Then it computes the same number. So this says that there's no way to distinguish these two programs by way of these contexts P. And I should note that there's other possible ways to do contexts P here. So if you look at the chapter on this in Bob's book, then contexts are defined in a little bit of a different way where they can be filled with programs that have free variables. And in some approaches to this kind of stuff, you'll take your contexts to be things other than programs at all, right? You might have more contexts that you can put programs in than programs that you have. And that represents the idea of you might have a program written in your nice language that you link with some outside assembly code or some foreign functions or something like that. And you might want to think about what happens when I link my program with something written in some other language. But for today, it's easiest to just assume that our contexts are terms with a free variable. So we'll do that to start up. Okay? So now our definition of equality is that two programs are equal if and only if you can't tell them apart. That is, whenever you build a bigger program out of them, you get the same answer when that bigger program is of type int. Okay, good on that? Questions? Okay. All right, so let's start a little running example. So suppose that I have the following two programs. The function that takes x and y and returns x plus y, and the function that takes x and y and returns y plus x. So I'll call this one plus and this one flip plus. And one question you might ask is, are these observationally equal? That is there any way to use these two functions that tells them apart? And you can guess that the answer will be no, right? Because what we're talking about here is some primitive addition on integers, and you expect that addition is commutative. Yeah?
How is observationally equal difference of structure equivalent?
So like, we can relate it to other words later in the lecture, but for now, like, the only thing on the table is this. Okay? We'll get lots of other equivalences over the course of the lecture. Okay. So that's thing one. And then thing two is, if I write some function that uses these, for example, suppose I write a function that sums a list of integers to produce an int by case analyzing L, and in the empty it gives back 0, and if the list has a head and a tail, okay, I need some functional language to write my programs in. I'll use SML, but hopefully you can translate this to OCaml or Haskell or Scheme or whatever if you know those. Then what I'll do is I'll call my plus function on x and adding up the tail of the list, right? So if I want to add together all of the things in a list, I add the head to the recursive call and the tail. Suppose, on the other hand, I write some, let's call it some prime, which is case L of empty goes to 0, or x cons x's goes to flip plus of x and some x's. Okay, so what have I done here? I've built a bigger program where on the one hand I used plus, and on the other hand I used flip plus. Right? So suppose we know that plus is equal to flip plus. Suppose we can prove that. Then what would we expect should hold automatically about these two? We would expect that those would be the same as well. Okay? So what I want to introduce here is a couple of ideas about observational equivalence, which is we want to use it to prove properties of particular programs. The simplest one I could think of is addition is commutative. And then we want to get for free some reasoning principles that say how we can use those facts once we already know them. Okay? So now let's develop a few facts about observational equivalence, which will let us do that kind of reasoning. So fact number one is that observational equivalence is characterized by a universal property. So this is foreshadowing something that Ed will talk about in the afternoon, or maybe tomorrow, which is an idea from category theory called universal properties, which is characterizing some class of things by the relationships between the things in that class. Okay? So the idea of observational equivalence being characterized by a universal property is that we can give a more convincing reason why that's a good definition of what it means for two programs to be equivalent. Well, how can I convince you if that's a good definition? Well, I can do some examples and say, okay, this is good for reasoning or something like that. But to some extent, right, like you might not have thought of this if I hadn't written it on the board. Oh, what we do is we start off by saying at base type they run to the same value, and then for any other type we say I extend it to base type by picking context. It's like a bit of a weird thing to come up with. So what we can say to convince ourselves that it's characterized by a universal property and therefore a reasonable or more convincing definition is that observational equivalence is the coarsest consistent congruence. Okay, so what do these things mean? Consistent means it implies Kleene equivalence at int. Okay, so if you have some relation on two closed programs, then to say that that relation is consistent means that if two programs of type int are related, then they're Kleene equivalent. Okay? Then they run to the same answer. Maybe I should write it since I see a few puzzled faces. So E1 being related to E2 at tau, or actually let me use E and E prime, is consistent if and only if E1 being related at int, E being related at int to E prime, implies that E is Kleene equivalent to E prime, i.e. E and E prime both run down to the same number. Okay, so our definition of a relation being consistent, if I have some binary relation, is that whenever it relates things of type nat, they actually run to the same number. Congruence means if E is related to E prime, then C of E is related to C of E prime for any, so let's say that's tau 1 and that's tau 2, for any context. And what is a context? For us, it's just going to be a program with a free variable, which I'll again write as the circle standing for a hole of type tau 1 that has type tau 2. Okay? So effectively what that's saying is that a relation is a congruence if whenever you have a function, right, think of a term with a free variable by the stuff discussed by Bob a few minutes ago is effectively the same as a function of one argument. Right? So you can think of a context as a function. What this says is a relation is a congruence if E is related to E prime, that means that C of E is related to C of E prime. Why would it be good if observational equivalence were a congruence? How do we get from this to this? Plugging it in. What's the context? C of the whole is the function sum of L, which is case L of empty goes to 0, or x cons x's goes to the whole applied to x and the recursive call on x's. right? So if I take that context, that term with a hole in it, the hole stands for what you do, sorry, that's a 0, and that's the hole, applied to the head and the tail. If I fill that with this, I get that. If I fill that with this, I get that. Therefore, if observational equivalence were a congruence, then knowing that plus is observationally equal to flip plus tells us that those two bigger programs that use each of them in corresponding places are equal. Okay? So what we want to know is that observational equivalence is a consistent congruence. And then corsist means if E is related to E prime by any consistent congruence, then E is observationally equal to E prime. Okay? So here's the idea. Yeah?
Why'd you define the C context? Isn't it the same?
So P, the only difference is that C is a program with a free variable of any type. I'll use P when that second type is specifically int. Okay? So a program context produces something of the ground type int. A general context produces something of any type. Okay? So the idea here is that this relation that we've defined in this way has the property that it's the biggest consistent congruence, where biggest means it relates the most things. Therefore, to show that two things are observationally equivalent, it suffices to show that they're related by any consistent congruence twiddle. So if you have any consistent congruence that relates to programs, then they're related by observational equivalence, which is to say, we've equated as many things as one possibly can while ensuring that two programs of type int actually run to the same value. So I mean, consistent means that if E is, if two things are related at type int, then they're cleanly equivalent. And congruence means if two things are related, then any bigger program you put them in, they're still, those two things are related. Okay, so this is the definition of congruence. This is the definition of consistent. Okay. Sorry, the board work got a little scattered there. Good? Other questions? Yeah.
So I feel like I've kind of seen this rewriting of the definition that you already gave of observational equivalence.
So it's almost the same. So right now we're going to prove that we're going to prove this. So this is an assertion. We're about to prove it. So I think when we prove it, like if the question is how is it different, then when we prove it, you'll see the gap. Okay. If the question is something else, then ask it.
Well, also are these ideas of consistent and congruence going to be useful outside of observational equality?
Yeah. Well, I mean, it's exactly this principle, right? So consistent congruence is saying that we can lift things. And then consistent says, for example, that suppose I have that the sum of the list 1, 2, 3, 4 is observationally equal to the sum of the list the sum prime of the list 1, 2, 3, 4, right? So when do you use consistency? It's when you've used your observational equivalence to prove a fact about two programs that actually have base type. And you want to know that, what does that mean? It means they actually run to the same number, right? Consistency is the thing that tells you that you're getting out some actual concrete information that's the same, okay? And so, I mean, if the question is, do these ideas get used when we use observational equivalence to reason about programs, then the answer is yes. Well, observational equivalence is kind of, what I'm trying to say is observational equivalence is the fundamental notion of equivalence of programs. So anytime you're reasoning about equivalence of programs, yes. Good? Yeah.
How is consistency different from functional?
Consistency is just saying when they're related at base type, then they're actually produce the same number. So that's, yeah. We'll get to something like functional extensionality in a little bit. OK, so that's a theorem. How do we prove it? Proof. Consistent. So what do we need to show? We need to show if E and E prime are observationally equivalent at type int, then E is cleanly equivalent to E prime. What does this mean by definition? For any context that you can put them in, P of E is cleanly equivalent to P of E prime. How do we go from two things are equal in any context you can put them in to what we want? Take P to be what? The whole itself. Because if I fill the whole with E, then that's equal to filling the whole with E prime. But substituting E for the whole is just E, and substituting E prime for the whole is just E prime. OK? So that's the identity context that gives us consistency. For a congruence, what we need to show is that if E is observationally equal to E prime, then any context we can put them in is observationally equal in the type the context kicks out to E prime. What does this mean? For all P, P filled with E computes the same answer as P filled with E prime. What does this mean? For all P prime, P filled with C filled with E computes the same answer as P filled with C filled with E prime. P prime filled with C with P prime. OK? Note that P here is the whole has type tau 1, and in P prime over here, the whole has type tau 2. Right? So we're talking about contexts with different holes in them, because P is a context that accepts E's and E primes, while P prime is a context that accepts those. So what we want to show is, for any way of completing C of E and C of E prime to a whole program of ground type, those two give the same answer. And what we know is, for any way of completing E and E prime to a program of ground type, those two give the same answer. So supposing we have such a P prime, how do we use this to get what we want? We take P to be the composition P prime with C plugged in for the whole. OK? Imagine that C is some program that sits around E and E prime. I can then put P around that. And the key point is that when I take this and I fill it with some E, well, that's going to, by definition, give P prime filled with C filled with E, which is what we wanted here. OK? So the fact that gives us congruence is composition of contexts. So it's really the properties of identity and composition of contexts that is the gap between this definition and knowing that it's a consistent congruence. OK? And now just to finish things off, how do we know that it's the greatest one? what we need to show is that if E and E prime, two programs, are related by any consistent congruence like that, then they're observationally equal. Well, take this. What does this mean? It means for any p, if I put E into p and I put E prime into p, I get the same answer. So how do I show that? By congruence, if I put E and E prime into p, they're related by this relation because it's a congruence. And the very definition of a congruence was that you can stick any context around two programs, and it preserves that relation. And then by consistency, if this relation is consistent, remember that P was by definition the kind of context that produces something of base type, of ground type there. So what I get by consistency is exactly that they're clean equivalent. Okay, so this definition over here has this universal property that it's characterized by being the greatest consistent congruence, the coarsest consistent congruence. And moreover, it's really the idea of identity and composition that give you this property. Okay, so now that we've got this property, what we know is that we've got this sort of more general way to use observational equivalences once we have them. Once we have them, we know that if I have two programs being observationally equivalent, I can take them, I can put them in any context, those two are the same. We know that when I actually conclude something about a number, it tells me a reasonable fact about a number, that is, they run to the same value. But in order to carry through this kind of argument, right, so this part would be congruence. Congruence would tell us because these programs are equal, these programs are equal. Consistency would tell us that, well, when I actually run them on some actual value and actually get something of type int, then they step to the same number overall. Right? So by congruence, I get takes equals to equals. By consistency, I get runs to the same number. How do I get started in the first place? Okay, so the missing piece is, how would I prove that plus and flip plus are actually equal functions in the first place? Well, we could try using the definition, right? Our definition of observational equivalence says that plus and flip plus are equal if and only if what? They evaluate to the same answer for all contexts P. Right? By definition, observational equivalence means I put them in some context that produces an int, and that gives the same answer. So in order to show this, so that we can get this by congruence and this by consistency, and therefore know that our functions actually produce the same answer on two actual inputs, all I have to show is that in any context in which you can put flip plus and flip plus, you get the same answer. Uh-oh. What does P include? It includes this context then applied to that actual value, right? Because P is any bigger program you can make out of plus and flip plus. Well, here's one bigger program you can make out of plus and flip plus. It also includes multiplying all the numbers in a list and any other program you might think of. Okay, you see the rub? This quantifier is a very strong thing, which means that knowing an observational equivalence is a very strong thing, but proving an observational equivalence is a very hard thing. Okay? Not only would we have to prove the thing we were trying to prove by congruence and consistency in the first place, we'd have to do all possible such proofs for all possible such programs in order to get that this thing runs the same as that. Okay? So we've defined when two programs are equal, but the thing we need to move to now is how do you actually prove it? And the key idea is to cut down the contexts that you need to consider using types. In particular, it should be enough to consider contexts of the form whole applied to M and applied to N for numbers M and N. Does that make sense intuitively? If I have two programs of type, what's the type of plus? The type of plus is it takes an int and returns a function that returns an int, and same for flip plus. Or it's, if you don't think about the currying there, it's a function that takes two ints and returns an int. Somehow it should be enough to check that these two functions are equal to just consider the contexts that apply them to two numerals. Because any other context, any other way of using those two functions should sort of be dependent on what the function does on numbers. This is exactly the kind of principle of function extensionality that someone mentioned before. It's the idea that to know if two functions are equal, if you're thinking of a function as a black box that takes inputs to outputs, somehow if you know that it does the same thing on all inputs, gives you the same output, that should be enough. Okay? So what we want to do now is to develop a way of reasoning about observational equivalence where to prove that these two programs are equal, all we have to do is check something like that. That is applications to numerals, because that's an easier problem to solve. We don't have to then solve this problem and all other problems like it in order to just figure out that these two functions are equal. Okay? So the goal is to introduce a notion where we can cut down what we need to know. And the notion that we'll introduce in order to do that is something called logical equivalence, which is essentially equivalence defined by this idea of logical relations that Bob used for termination in the previous lecture. So here's the idea. We're going to characterize when two programs are equal, not by a universal property like this, but by what type they have. In particular, E is going to be logically equivalent to E prime at type int if and only if something. And E is going to be logically equivalent at type tau1 arrow tau2 to E prime if and only if something else. That is, the definition of when two programs are equal will depend on what type they have. Okay? And the key theorem is going to be that E is observationally equal to E prime if and only if E is logically equivalent to E prime, which is going to say that this is the definition. This is a very useful thing for once you know that two things are equal. But this is what we'll use to establish that two things are equal. Okay, so we're going to have two different definitions that amount to the same thing. One will be good for proving things. Another will, to a first approximation, be good for using things. Okay? If we have that, then we can solve the problem of plus being related to flip plus, because instead of proving that they're observationally equivalent, which meant that, what we'll do is we'll prove that plus is logically equivalent to flip plus at type int, arrow, int, arrow, int. And after a little bit of massaging, that'll mean that it sort of suffices to check that kind of thing. Okay? So what we're doing is we're setting up another definition, which is easier to establish. We want it to mean the same thing as this. So what should we say for int? Well, we want logical equivalence to be the same as observational equivalence. Observational equivalence is the greatest consistent congruence. Therefore, logical equivalence had better be consistent. That is, it had better relate to things at type int. That had better imply Kleene equivalence. There's a question of whether you want that, right? Maybe we need to impose some stronger conditions to get a proof to go through or something like that. But at a first cut, we can take that to be the definition and say that. When should two functions be equal? What context should we need to consider for functions? Well, what we want to say is that for all closed E1 and E1 prime of type tau 1, if E1 is logically equivalent to tau 1, to E1 prime at tau 1, then the function application E1 is logically equivalent at tau 2 to E prime E1 prime. Which is to say, two functions are logically equivalent if, and only if, they take equal arguments to equal results. Okay? This is a way of codifying that it should be enough for functions to consider contexts that consist of applications. Okay? So I won't work it out, but from this definition, if you just expand out what it means, okay, maybe I'll do a little bit of it. So what does it mean for plus to be equal to flip plus? That means for all E1, which is logically equivalent at int to E1 prime, plus applied to E1 is logically equivalent at int arrow int to plus applied to flip plus applied to E1 prime. And what does that mean in the next round? That means for all E2, which is logically equivalent at int to E2 prime, plus applied to E1 applied to E2, is logically equivalent at int to flip plus applied to E1 prime applied to E2 prime. Okay, so you see how I'm expanding the definition there? Every time you have an arrow, you say, assume I have two equal arguments, apply both sides, check that they're equal. We do that for the first argument to plus, and then for the second argument to plus, and we get that. What is the definition of logical equivalence at int? Well, that's just cleanly equivalent. So that and that and that mean that those run to the same thing. So what we have overall is this picture. E1 and E1 prime run to the same number. E2 and E2 prime run to the same number. And we want that plus E1, E2, and flipped plus of E1 prime, E2 prime run to the same number. Okay, so what we've got is that E1 and E2 have the same numeral value. E1 and E1 prime have the same numeral value. So do E2 and E2 prime. And we need to know that plus E1, E2 and plus E1 prime, E2 prime have the same number. If you just think about how the operational steps work, what this amounts to, if you just do some basic syntactic reasoning, is that, well, remember, it's erased now, that plus was just the function that applies the plus, built-in plus to those in order, and that was to that flipped. So what we get is that we need to show that m plus n is cleanly equivalent to n plus m when those are actual numerals, and that's the actual plus. And that's basically a proof by induction if these are real natural numbers, or if these are 32-bit machine words, then it's a proof by 2 to the 32 cases that says that the operation does the right thing, right? It's just boiled down to base type. Okay, so the idea is that we now have a much better way to show that these two programs are equal. And admittedly, I'm taking the smallest example I could think of, right? So over the course of the next couple of weeks, we'll see how this scales to much bigger examples. This was the smallest one I could think of to introduce the concept. We have a good way to show that two programs are equal without solving all possible problems at once. We just do it for some very small contexts, because logical equivalence says, depending on the type, you only need to check certain contexts. Okay? So what we've seen so far is that observational equivalence has a strong universal property. It's a good thing to use. Logical equivalence is a much finer definition on the face of it, but really should include all of the same things. But that's what we need to prove, right? So where's the work going to go? The work's going to go in proving that logical equivalence and observational equivalence actually do coincide. Okay, so let's set that up. Where do I want these? Okay. Which of these should be easier and which of these should be harder? So what does observational equality mean? It means for all contexts, they're equal. What does logical equivalence mean? To gloss it, it means for some very carefully chosen contexts, they're equal. Right? Observational equivalence was, in any context you can put them in, they're equal. Logical equivalence was, I've picked out some certain contexts, and I'm guessing that that's enough. Okay? So which direction of this should be easy? That one should at least be easier. There's a bit of a twist to it, but because that one's easier, I'll leave it as an exercise for the hands-on session. Why? Because essentially it says, if they're equal for all contexts, then they're certainly equal for those two particular contexts that I've picked out on the basis of the type there. So the thing I want to focus on is this direction, which is the harder one, which is to show that when two things are logically equivalent, they're in fact contextually equivalent. Good? All right, so what can we do to show that logically equivalent things are observationally equivalent? Well, what do we know about observational equivalence? Remember, logical equivalence is the coarsest consistent congruence. So what can we show in order to know that logical equivalence implies observational equivalence? All we need to show is that logical equivalence, so it suffices to show that logical equivalence is a consistent congruence. And then by what we did 20 minutes ago, it implies observational equivalence. Because we said observational equivalence is the consistent congruence that relates the most things. Therefore, if this is a consistent congruence, then it implies observational equivalence. Oh, question? Yeah. OK. OK, good. Is it consistent? We basically rigged it to be consistent by choosing that as the definition at int. So what we really have to worry about is that logical equivalence is a congruence. OK? So how do we show that logical equivalence is a congruence? What we need to show is that for all programs with one free variable c, if E is logically equivalent to E prime, then C filled with E is logically equivalent to C filled with E prime. Right? Because that was our definition of congruence. OK? How might you think to prove this? What could you do induction on? You could do induction on, there's basically three things. That, or that. OK? So we could try any of those. The thing that actually gets you part of the way towards the right answer is to try C. Okay? The idea is what we need to check. Remember, logical equivalences, they're equal in some contexts. Observational equivalences, they're equal in all contexts. Therefore, what we need to do is to check for all contexts, in fact, it works over here. Why does it work over here? Because any other context is essentially this kind of specially chosen one on top of, right, can be sort of a composition with this kind of specially chosen one. Okay? So what we would want to check is by induction on programs with one hole in them, this works. By analogy with Bob's version 3 from earlier this morning, it's not going to be enough to do induction on programs with one free variable. Why? As soon as you start to crawl over programs with one free variable, you go under a lambda, or you go under a case, or you go under an iter, suddenly you've got two free variables. Okay? So we're going to need a generalization, which is actually kind of a little bit easier to think about, which is if we have any well-typed program at all and something, then E something is related to E something. OK, clearly we've got a little bit to fill in. So if we want to generalize this statement for any program with one free variable, if you plug in logically related things, then you get logically related things to many variables. Then what we need is this idea of a substitution, which is of the form E1 for x1 all the way through En for xn. And then we'll write gamma prime for E1 prime for x1 all the way through En prime for xn. OK, so think of a substitution as this as things to plug in with, like, you're going to have a whole bunch of them at once. OK, so for each variable, when we have a context gamma being of the form x1 has tau1, x2 has tau2, all the way through xn has tau n, what we want here is that we have a term of each corresponding type to plug in. OK, so I'm just going to iterate that. And what I need to do is I need to define gamma is logically equal to little gamma prime at gamma if and only if what Bob wrote as gamma hat of x is logically equivalent at tau to gamma prime of x for any x colon tau in gamma. OK, so in the hands-on session, you can look at the math of it. Here's the idea. We have two contexts which list a bunch of free variables. We have two different sets of things to plug in for each of those two free variables, gamma and gamma prime. And we insist that they match up pointwise. So whatever I plug in for x over here is related to whatever I plug in for x over here. Whatever I plug in for xn over here is related to whatever I plug in for xn over here, which is just iterating this idea of I have two things to plug in for one variable, and the results are equal. OK? And so then what we say is if gamma is logically equivalent to gamma prime, then when I actually do the plugging in over there, and when I actually do the plugging in over there, then they're equal. OK? So this is getting a little technical, and it's the kind of thing that you really have to work through for yourself. But the idea is just, I start with my idea of it's a congruence, which is for any program with one free variable, plugging in equal things gives me equal things. And I extend that to many variables at once and say, when I plug in equal things for the many variables where they're equal pointwise, then I get equal things.
What does the gamma hat represent?
So gamma hat is the notation for applying a substitution to a term and actually crawling over the term. And wherever you see x, you put in the e that was sent for x in the substitution. OK, so it's the action of gamma on the term. Good? OK, and now we've got something that we can actually prove, which is this. This is often called the fundamental theorem, or sometimes the fundamental lemma of logical relations. And so what it's saying is that whenever you have a well-typed program, it's in the relation. And in particular, you always generalize that to whenever you have a well-typed program, it takes related things to related things. OK, and now we're basically set up to crank through some cases. OK, so where should we start? How about gamma x colon tau proves x colon tau? Because what we're doing now is, of course, induction on the typing derivation, which tells you that the program E is well typed. One of the cases is this is a variable. Well, what we need to show is that gamma hat of x is logically equivalent to gamma prime hat of x. That is, whatever I substitute in here, right? So this will, among other things, include an e for x. And this will, among other things, include an e prime for x. And what I need to show is that this is equal to that. But by definition, gamma hat of x is equal to that e, and gamma hat prime of x is equal to that e prime. Right? When I actually do substitution, what I get for a variable is, by the definition of substitution, whatever I said I put in for that variable. How do I know that these two things are related? So therefore, I need to show that e is logically equivalent to e prime in tau. Why is that the case? That's my assumption, right? My assumption is that I'm plugging in logically related things for the variables. Whatever I plug in on the left for one variable plus is equal to whatever I plug in on the right for a variable flip plus. So we're good. Okay? So the variable case, you basically set up the form of the theorem so that the variable case falls out from the assumption because you've got enough assumptions about what you're plugging in that you can do it. Okay, next case. Let's try suppose that we have E is tau 1 arrow tau 2, and E1 is that, and, or let's try E being that, and E1 being tau 1. Therefore, the function application E of E1 is of type tau 2. Okay, so if that's our typing derivation, and we have that gamma is equal to gamma prime, what do our two inductive hypotheses on that and that tell us? Well, we just apply the theorem statement to those things. And what we get is that E, the function position with gamma, is logically equivalent in tau 1 arrow tau 2 to E with, oh, sorry, I'm switching my notation. Gamma of E is logically equivalent to gamma prime of E in tau 1 arrow tau 2. That is, when I plug into E, I get related things. And 2 is that when I plug into E1, that's logically equivalent in tau 1 to plugging in with gamma prime in E1. Right? By induction, the function position takes equals to equals, takes related things to related things. The argument position takes related things to related things. Therefore, here I get related functions, and here I get related arguments. What is the definition of substitution into an application? If I'm trying to search and replace all the variables in a function application, well, by definition, that's search and replace in the function position, search and replace in the argument position, which means it suffices to show that gamma of E applied to gamma of E1 is logically equivalent in tau 2 to gamma prime of E applied to gamma prime of E1, right? Because by definition, what I want to show is that the function application itself acts as a congruence. The definition of the function application on an argument, on a substitution, is find all the things in the function position and in the argument position. Therefore, I get this And how do I get from here to here?
Look at the definition of logical equivalence for functions.
We know that this function equals this function. We know that this argument equals this argument. We want that this function applied to this argument is equal to this function applied to this argument. The definition of logical equivalence for function types is it takes equal functions, two functions are equal if and only if, when applied to equal arguments, you get equal results. So this is exactly the definition of being logically equivalent in arrow. Okay? Because I knew where I was going in the proof, I rigged the definition of equality in the type to essentially say, when you apply an elimination form application, you get equal results. Okay? That's kind of the method that's going on behind the scenes here. We'll see some more instances of it soon. Okay, so we're done with the case for application, right? We've shown that application preserves equality. So all we have left is, well, the cases for numerals and addition, which I'll let you do in the hands-on session as an exercise, and one more case, which is the case for functions themselves. So suppose I have lambda x dot e has type tau1 arrow tau2 because lambda x colon tau1 proves e colon tau2, and I have gamma being related to gamma prime substitutions for gamma. Okay? What do I want to show? I want to show that lambda x dot e with the gamma substitution applied is the same as lambda x dot e with the gamma prime substitution applied in tau1 arrow tau2. Okay? So there's two moves we need to make here. One, what is a substitution into a function? There's a little bit of messing around with variable binding that we have to do here, but the definition is essentially this. It's the function that applies gamma to e. Okay? There's a side condition here, which is that you want to make sure variables don't get confused, but if you look at the chapters on ABTs and the whole setup, you can always satisfy that side condition so that we can push things inside there. Okay, so now, based on that, this holds if and only if lambda x dot gamma applied to e is logically equal in tau1 arrow tau2 to lambda x dot gamma prime applied to e. Notice that what we're trying to prove now is that these two functions are equal. What does it mean to prove that two functions are equal? It means assume E1 logically equivalent in tau1 to E1 prime. And from that, we need to show that lambda x dot, the substitution instance of E applied to E1, is logically equivalent in tau2 to lambda x dot, the substitution instance of prime of E applied to E1 prime. That is, the one function applied to the one argument is equal to the other function applied to the other argument as long as these two arguments are equal. Okay? How are we going to get that? What do we have here? we have a function applied to an argument. What does a function applied to an argument do? That's exactly the execution step for the function type. So this will take a step in order to get to the substitution that plugs in gamma and E1 for x applied to E. And this side will take a step to the function, the substitution that does gamma prime and E1 prime for x applied to E. Okay? So what I'm trying to say here is this executes to that, this executes to that. When I have a function applied to an argument, the step rule that Bob wrote on the board first thing this morning was that you take this and you plug it in for the argument. And by a little bit of massaging of substitutions, what you get is that that substitution of first doing gamma and then doing that is the same as doing simultaneously gamma and then E1 for x. So by execution, what we get down to is that we need to know, therefore, that these two things are equal. But lo and behold, what do we have? We have a program E with those free variables. And we have that gamma comma E1 for x is logically equivalent in that extended context to gamma prime E1 prime for x. Why is that? What does logical equivalence for our context mean? It means all of those match up, which we know by that. And it means those match up, which we know by that. So we can keep the induction going and go under the binder. And by the inductive hypothesis, we get that these are related substitutions, equal substitutions. And therefore, by the theorem we're trying to prove, E, substitution 1, substitution 2, when substitutions 1 and 2 are equal, are themselves equal. Okay? So we use the inductive hypothesis in the extended context, keeping the fact that the substitutions are equal going like this in order to get the result. Yeah? Okay. Okay, so that's basically the idea, except there's one fact that I used here without really justifying, which is that. Okay? Why is it the case that I can massage by execution in this proof? And so the lemma that we need is something called closure under converse evaluation, which says that if E steps to E0 and E0 is logically equivalent to E prime, then E is logically equivalent to E prime. Okay? That is, we can pull a logical equivalence back along a step and get a logical equivalence. Because we get that these two are logically equivalent by the IH, and then assuming this lemma, we get that these two are equal by the lemma, and that's what we needed to show in this case. So that closure under converse evaluation is something you have to prove by induction on tau, and that'll be one of the problems in the handout for the hands-on session today. Yeah.
How much of that could be simplified if we were to recognize that observation equivalence is made up?
Yeah, I mean, so like what I'm trying to do here is to give you sort of the kind of most syntactic from first principles what you would invent view of all of this. The next course by Patricia Johan in the next set of lectures is going to be a very high-level account of all of this. So like, I wanted to just sort of get the basic syntactic stuff on the table first, but there's ways to kind of systematize all of this. OK, so just to wrap up, since we're out of time, what we've got going now is we've got observational equivalence as the coarsest consistent congruence characterized by universal property tells you what it really means for two programs to be equal. We've got logical equivalence established as a tool for proving observational equivalences with the key idea that by induction on the type, you can select specific congruences, specific contexts to consider. And so we're going to play this same game tomorrow, but for a much fancier language, in order to characterize observational equivalence for things with polymorphism. OK, so in the hands-on session, you should really start to look at some of this. I'll do a handout that has some good first exercises to do. But trying to get your head around some of this logical relation stuff before tomorrow would be very helpful. OK, thank you.